Imagine shrinking the world's most powerful particle colliders down to the size of a single molecule. That's exactly what physicists have achieved, offering a groundbreaking new way to peek inside the heart of an atom's nucleus. Traditionally, scientists have relied on massive, kilometer-long particle colliders to smash atoms apart, like the Large Hadron Collider, accelerating electrons to incredible speeds to probe the nucleus. But these facilities are complex and costly. Instead, researchers have devised a clever, miniature alternative. They've essentially turned an atom's own electrons into tiny messengers within a molecule, allowing them to gather data from the nucleus without the need for colossal machinery. How did they do it? By creating a molecule of radium monofluoride, pairing a radium atom with a fluoride atom. The key lies in the unique properties of this intramolecular environment. It's like building a microscopic particle collider, where the radium atom's electrons briefly venture into its nucleus. This allowed the scientists to meticulously monitor the energies of these electrons, revealing subtle shifts. These shifts indicated that the electrons were, in fact, interacting with the nucleus's contents. This innovative approach could revolutionize how we measure the magnetic distribution within a nucleus, revealing how its arrangement of protons and neutrons influences its magnetic properties. This is a crucial first step, and the researchers are already planning to use this technique to further investigate the radium nucleus. But here's where it gets controversial. This research could help solve some of the biggest mysteries in physics, such as why the universe seems to be dominated by matter, with very little antimatter. Current models suggest that the early universe should have contained equal amounts of both. The fact that matter vastly outweighs antimatter today is a significant puzzle. Scientists suspect the answers may lie within the atomic nuclei. Radium is a particularly promising candidate due to the unique, pear-like shape of its nucleus. Unlike most atomic nuclei, which are spherical, radium's asymmetry might amplify the observability of fundamental symmetry violations. Our results lay the groundwork for subsequent studies aiming to measure violations of fundamental symmetries at the nuclear level, says MIT physicist Ronald Fernando Garcia Ruiz. This could provide answers to some of the most pressing questions in modern physics. However, it's not all smooth sailing. Radium is naturally radioactive, with a short lifespan, and the researchers can only produce radium monofluoride molecules in tiny quantities. Therefore, incredibly sensitive techniques are needed to measure them. When you put this radioactive atom inside of a molecule, the internal electric field that its electrons experience is orders of magnitude larger compared to the fields we can produce and apply in a lab, explains co-author Silviu Marian Adrescu, a physicist at Johns Hopkins University. In a way, the molecule acts like a giant particle collider and gives us a better chance to probe the radium's nucleus. Within the radium monofluoride, the radium atom's electrons were constrained in a way that boosted their chances of entering the nucleus. Researchers confined and cooled the molecules, then used lasers to measure the energies of electrons inside them. Minute but significant shifts in the data hinted at adventures inside the nucleus. There are many experiments measuring interactions between nuclei and electrons outside the nucleus, and we know what those interactions look like, says Shane Wilkins, lead author and physicist. When we went to measure these electron energies very precisely, it didn't quite add up to what we expected, assuming they interacted only outside of the nucleus. That told us the difference must be due to electron interactions inside the nucleus. We now have proof that we can sample inside the nucleus. It's like being able to measure a battery's electric field. People can measure its field outside, but to measure inside the battery is far more challenging. And that's what we can do now, Garcia Ruiz says. And this is the part most people miss. This discovery could dramatically change how we study atomic nuclei. It's like having a new, incredibly precise tool to unlock the secrets of matter and antimatter. Radium-containing molecules are predicted to be exceptionally sensitive systems in which to search for violations of the fundamental symmetries of nature. Garcia Ruiz adds, "We now have a way to carry out that search." The study was published in Science. What do you think? Could this new approach revolutionize our understanding of the universe? Do you have any questions about this fascinating research? Share your thoughts in the comments below.